So far, we have a simple equation that helps us predict the travel time based on the number of miles driven. From the r squared, we saw that the number of miles helps us to predict about 66.4% of the variation in the travel time. There is still some variability that is left unexplained. That is 100% minus 66.4%, 33.6%. That is left unexplained. We want to improve this model. That is, we want to reduce this unexplained variability by adding some other factor that could help explain the variation. One obvious factor we might include is the number of deliveries in the driving assignment. Some assignments might include more than one delivery, and every time the driver stops to make a delivery, it adds to the travel time. Let's suppose that after the managers of Butler Trucking decide to add the number of deliveries into the model, they collect new observations for the next few weeks. In the Excel file, we're given a sample data of 300 observations. The first few assignments are shown here. Here we have two independent variables to help us predict the travel time, miles traveled and the number of deliveries. For instance, assignment 1 took 9.3 hours total. This time included driving 100 miles in the route and making 4 stops along the way to make deliveries. Assuming the relationship is in a linear form, we're looking for an equation like this. This is a multiple linear regression because we have more than one independent variable. B sub 0 is a constant form as before, and B sub 1 is the coefficient or the slope for the distance, and B sub 2 is a coefficient for the deliveries. These B sub 1 and B sub 2 tell you the effect of the respective x variable on the y variable. The concept here is, again, we're using the sample data to estimate the regression model in the population. Here's a general form of multiple regression model with, say, q independent variables. Betas are the parameters, that is, the coefficients to be estimated. The epsilon is the error term, that variability in y that is not explained by the combination of these q independent variables. For any given combination of the x values, the mean of the y value can be expressed like this without this error term. Again, remember, this equation is for the entire population of driving assignments, past, present, and future. Since we don't have the data for the entire population, we're going to have to rely on our sample data, like the 300 observations we have, to estimate these betas. When we use our sample data to estimate the betas, we need to switch from the Greek letters to the Roman letters. The Roman letters, B's, indicate they were estimated from the sample data. They are called the point estimates of the betas. In estimating the regression coefficients, we use the least squares method as in the simple regression. That is, we find the B values that minimize the sum of the squared errors. As before, the error for each data point is the observed y value minus the estimated y value. You could see here the whole expression for the y hat is subtracted from the y value. To estimate the regression equation for Butler Trucking, we're going to use the data analysis feature in Excel. Now here we are in Excel. We're going to go to Data tab, then the Data Analysis. We're going to select the regression here. Okay. In the regression dialog box, we're going to enter the Y range and the X range, including the column headers, that is, the column titles. So we select the column title for Y, Control-Shift-Down arrow to select the entire column of data. Then, to return, we hit Control-Backspace. Okay, now let's go to the X range. choose the 2 column titles, Control Shift down arrow, then Control backspace. Now we check the labels box to indicate that we included the column headers in the data we entered. We always want to include the column headers so that the output we get will be labeled properly with the variable names. Now if I click on OK now, it'll give the regression output I need in a new worksheet, and that is enough. The other items are for checking the validity of the regression equation we will get. Since we'll be talking about assessing the regression equation, we're going to ask for some of these other items. For each regression coefficient beta, the output will give you not only the point estimate B, but also the confidence interval around it. The width of the interval depends on how much confidence you want. That is why it's asking what you want. It actually gives you 2 sets of confidence intervals. It'll give you 95% confidence interval by default. If you want the second set of confidence intervals with some other confidence value, then you could enter it here. If you leave this unchecked, the second set will also have confidence level of 95%, which is a bit silly. We'll just try entering 99% here. So check 99. Now let's ask for some other things. The residuals here will give you the residuals for the sample data along with the predicted y values. And the residual plots here will give you the plot of the residuals against each x variable. And line fit plots will give you the scatter plots of the dependent variable y versus each x variable. Okay. Here it is. Well, this looks a little messy. We're going to have to adjust the width of the column to be able to show everything inside the cells. So we're going to, we select the columns of the output. Then we could double click on edge of any of these columns to automatically adjust all the column width to show all the contents. We could also rearrange these plots so we could see all of them, and maybe make them a little bigger. So what is a regression equation? Well, we have the coefficients for our regression here. So here is the b sub 0, here's b sub 1, and b sub 2. We have a lot of decimal digits shown here. It is a bit too much. Usually you want to show them rounded to the 3rd or 4th decimal digit. Well, we could just get Excel to round them for us. So we select the values and just decrease the decimal until we get, let's say, 4 decimal digits. Now we could write the equation. Y hat is equal to 0.1273 plus 0.0672 times x sub 1 plus 0.6900 times x sub 2. Actually, it's better to use the variable names or the column titles. So we could say estimated time in hours is equal to 0.1273 plus 0.0672 times the number of miles plus 0.6900 times number of deliveries. Now let's see how we would use this equation to make predictions. Suppose our next assignment involves driving 80 miles with 4 deliveries. How long do we expect this trip to take? Well, we plug in 80 here for the miles and 4 for the deliveries. So 0.0672 times 80 gives us 5.376, and 0.69 times 4 gives us 2.76, and adding these 3 values together gives us 8.2633 or 8.26 hours. Now how about 80 miles with 5 deliveries? Well, that's one more delivery than this driving assignment, right? The same number of miles. So then we would expect it to take 0.69 hours more than this previous assignment. How do we know that? Well, because 0.69 is a slope for the deliveries. That is, it gives you the increase in the time per unit increase in the number of deliveries. So it'll take the original time, 8.26 hours, plus 0.69 hours, or that works out to be 8.95 hours. Now, what if you have a driving assignment with 80 miles and 3 deliveries? Then it should take 0.69 hours less than before. So you would do 8.26 minus 0.69. So that's if you have 3 deliveries. So we could say in general, each additional delivery adds 0.69 hour, or that's about 41 minutes, to the travel time. This is without changing the distance traveled. So if the distance traveled remains the same and the number of deliveries changes, that effect is given by the 0.69 per delivery. Now, what if you have another assignment with 70 miles and 4 deliveries? In this case, the number of deliveries stays the same, but the number of miles has decreased by 10. Well, according to the regression coefficient here, each mile contributes about 0.0672 hours to the travel time, or let's say if I multiply by 60, that's about 4 minutes. So if you travel 10 fewer miles than before, then the number of hours should decrease by 10 times 0.0672 hours, which is what? 0.672. So it will be 8.26 hours minus 0.672, which is 7.59 hours. Of course, we could do this calculation more easily in Excel. Here are the coefficients we could use. We're going to copy and paste these in the empty space here. Here the coefficients are in a column form, but I think it's even more convenient to put them in a row form. So we're going to transpose from column to row as we paste. So let's select the 2 columns, including the labels, and Control-C to copy. And I'm gonna go, let's say over here, then right click and look for the, under paste options, the little icon here for transpose. So again, I went right click, then under paste options, I see here the transpose icon. So click on that. Here it is. Now we'll try the assignments from the slide. So let's see. Here we had 80 miles and then 4 deliveries. Then we had 80 miles and, what was it, 5 deliveries. And let's go to 70 miles and then back to 4 deliveries. And here we're going to put the estimated time. Since we're going to do several calculations, we're going to use dollar signs around the reference to the coefficients in our formula. Okay, for 80 and 4, intercept dollar signs plus coefficient dollar signs times x1, so b1 times x1, and plus b2 times x2, so that's your b2 dollar signs times x2. Okay. So here's p sub 0 plus p sub 1 times x1 plus p sub 2 times x2. Okay, 8.26, right? So that's the same value we got before. Then I'm going to just copy this down to get our estimates. Now keep in mind the coefficients here are shown rounded to 4 decimal digits, but in calculations it doesn't use the rounded form. You could see if you click on the cell, the stored value in this cell is not rounded. So when it does a calculation, it'll use all these decimal digits. So the result could end up being a little different from the manual calculation, where you're using the rounded format of each coefficient. At this point, I want to make sure we understand how to interpret the regression coefficients by trying a couple of other examples. These examples will have negative regression coefficients. Let's suppose we have data of racing bikes, and for each bike we have the weight of the bike and the price of the bike. For racing bikes, lighter bikes have better performance, so they are more expensive. So a regression equation could look something like this, with a negative coefficient for the weight. First, let's make a prediction of a bike that weighs 20 pounds. We plug in 20 pounds for the weight. Multiplying 20 by 58.61 gives us 1172.20. So subtracting this from 1732.45 gives us $560.25. So that would be the predicted price. Well, what happens to the price as the weight increases? Well, since the slope here is negative, negative 58.61, the price will decrease as the weight increases. So let's say you have weight of 21 pounds. We could write this relationship like this. Bike price is equal to 1732.45 minus 58.61 times the weight is 21, so it's 20 plus 1, which is the same as 1732.45 minus 58.61 times 20, and minus 58.61 times 1. Now this part was the original price, so that's 560.25, then minus 58.61. So that gives us a price that's less by 58.61, or 501.64. So we could see when the weight increases by 1, then the price goes down by 58.61 because of that negative coefficient. How about for a bike that's 2 pounds lighter, say weight of 18 pounds? Then the price should increase by 2 times 58.61. So we could think of it as the original price minus 58.61, and then the change in the weight is negative 2, decrease of 2, so it's kind of like this, which is actually increase of 117.22. So the price of this lighter bike would be 560.25 plus 117.22, resulting in the price of $677.47. Here's another example. Let's say you work at a bank that issues credit cards. You would like to have customers that charge a lot on your credit card so you could collect more fees. So you came up with a regression equation that predicts how much a customer will charge on your credit card annually based on their income, household size, and years of post-high school education. Let's say you have a new customer who has 4 years of college education, who is married with 2 children, with an annual income of $80,000. We want to predict the annual charges for this customer. So it would be 2051.64 plus 120.63 times the annual income in thousands of dollars, so that's 80 times 80, plus 533.85 times the household size. Well, now this person is married with 2 children, so there must be 4 people in the household. So multiply by 4, then 505.63 times the years of post-high school education, so that's 4 years after high school. So multiply by 4. This kind of calculation is a bit tedious, so I'm going to use Excel. I have the coefficients set up here. I plug in the x values, 80,004 and then 4. I'm going to put a 1 here. So what I want to do is I want to multiply each coefficient by the value and then add the results. So I'm going to use a sum product function. I put dollar signs around the reference to the coefficients just in case I want to repeat this calculation later. So what this sum product function will do is it will multiply the corresponding pair between the 2 arrays and then add the results, which is what we want. So the answer is 11814.92. I'm going to write that down. Now let's say you have another customer who makes the same amount of money and the same number of people in the household, but went to the graduate school for 2 years. So post-high school education is 6 years for this new customer. Without plugging all the values again, we could just look at the coefficient of the post-high school education right here. The coefficient, negative 505.63, says, for each additional year of education, the annual charge will decrease by $505.63. So for 2 more years of education, the charge will decrease by 2 times 505.63. Let's write that down. So now the new predicted Y is the old value minus 505.63 times 2, or 1011.26, and that gives us 10803.66. Of course, this works only if the other x variables are fixed. Let's say you have another customer. Now this person makes $70,000. There are 4 people in the family and 6 years of post-high school education. If I wanted to get the predicted Y value based on the original Y value here, I could add up the changes based on the respective regression coefficients. So the annual income went down from $80,000 to $70,000, so that's $10,000 difference, or decrease of 10 in the variable value here. So it would be 120.63 times negative 10. Now the education years has increased by 2 from 4 to 6. So effect of that is the coefficient negative 505.63 times increase of 2, and with this product being 1206.3 and with this one being 1011.26, the resulting annual charges is 9597.36. Well, we could check this also by plugging in numbers into Excel. $70,000 for the annual income, 4 people in the household, and 6 years of post-high school education. And copy down this formula, 9597.36, and that is correct. Now that we have had some practice in interpreting the regression coefficients, we'll go back to the Butler example. Now let's go over to the table on the top and discuss the R squared. Well, first, we're going to adjust the number of decimal places here. Also, we'll go to the second table titled ANOVA and fix the decimal places. Parts of these two tables are shown on a slide here. The R squared is 0.8173, and this tells you the proportion of the variation in y explained by the x variables. So that is, we'll say 81.7% of the variation in the travel time is explained by the multiple regression, that is by the miles traveled and number of deliveries together. How much variation still remains unexplained? Well, it will be just 100% minus 81.7%. So 100 minus 81.7% is 18.3%. As before, R squared can be obtained as the ratio of SSR and SST. The sums of squares are given in the second table here. Here is the SSR, sum of squares due to regression. Here is the SSE, sum of squares due to error, and the total sum of squares, SST, is here. So you see, if you divide 915.516 by 1120.103, you will see we get 0.8173 as the R square. These sums of squares are computed the same way as before. Calculations of all these sums of squares were all done for us, so you don't need to know how to calculate these sums of squares, but I will give you a quick look into the details anyway. You will not have to do the calculations yourself, but understanding how these values were calculated could help you understand and remember the concepts. Here are the details of the calculation. First, you could see that these columns represent the given data. Now this column gives you the predicted y values, as you could see here. You could see that the x variables are plugged into the regression equation. 0.1273 times 0.0672 times x1 plus 0.69 times x2. The next column gives us the residuals, or the errors, the observed y values minus the predicted y values. To get the sum of squared errors, we need to square these values and sum them. And here is a shortcut function, SUMSQ, for doing just that. So squared and then sum the squares. So that gives us 204.587, which you already saw before. The next column gives you the observed y value minus the mean y value. Now the mean y value is over here, 7.28. And here you could see we have observed minus the mean. Again, squaring and summing the results gives us the SST as shown here. And the last column has the predicted minus the mean values. And squaring and summing gives us the sum of squares due to regression, 915.516. We're also given here multiple r as 0.9041. What do you think this figure is? Oh, it says right here, it's a correlation coefficient between observed y and predicted y. Remember, in the simple regression, the r was the correlation coefficient between the y and the x variable. In a multiple regression, it's between y and y hat. which is the combination of the x variables. To see this, let's go over to the sheet with the details. Here are the observed y values and the predicted y values. Taking the correlation of these two columns gives us the 0.9041. Also, as before, you could get the r by taking the square root of the r squared, as you could see here. So either way, we get the same value, 0.9041.